Have you ever wondered how a nuclear reactor, a powerhouse of energy, works? This marvel of modern engineering is not as mysterious as it might seem. Today we're going to peel back the layers and delve into the heart of these energy giants. We'll explore the intricate processes that take place within these steel walls, from the splitting of atoms to the generation of heat and electricity. So strap in, science enthusiasts, as we prepare for an enlightening journey into the heart of a nuclear reactor. At its core, a nuclear reactor is a machine that harnesses nuclear energy. So, what exactly is nuclear energy? Well, it's the energy held within the nucleus, the very heart of an atom. This energy is derived from the forces that hold the nucleus together, and it's so potent that it's responsible for everything from powering our cities to fueling the stars. Now, how do we unlock this energy? It's not as if we can just crack open an atom and let the energy pour out. Actually, it's a bit more complex than that. There are two main ways to release nuclear energy: nuclear fission and nuclear fusion. Nuclear fusion is the process that powers the sun and other stars. It's the combination of lighter atomic nuclei to form a heavier nucleus. This process releases a staggering amount of energy and is what keeps our sun burning brightly. However, achieving fusion here on Earth is incredibly difficult and requires conditions of extreme heat and pressure that are challenging to sustain. That's where nuclear fission comes in. Nuclear fission is the process of splitting a larger atomic nucleus into two or more smaller nuclei, along with some byproducts. These byproducts include free neutrons and photons, usually in the form of gamma rays, and a great deal of energy. This process begins when a neutron strikes the nucleus of an atom, causing it to split and release more neutrons, which then strike other nuclei, creating a chain reaction. The beauty of nuclear fission is that it can be controlled. By carefully managing the number of free neutrons, we can maintain a steady chain reaction, releasing a constant stream of energy. This is the principle behind a nuclear reactor, which harnesses the energy from fission to produce heat, which can then be used to generate electricity. The type of nuclear energy we are focusing on today, the one used in power plants, is nuclear fission. So, let's dive deeper into how this process powers our world. Nuclear fission, the splitting of an atom, is the heart and soul of a nuclear reactor. This process starts when a neutron, a subatomic particle with no electric charge, strikes a uranium atom. Uranium, specifically uranium-235, is often used because it's a fissile material, meaning it can sustain a nuclear chain reaction. Now imagine a billiard table where the cue ball is our incoming neutron. It strikes the 8-ball, our uranium atom, with just enough force to break it apart. This is what happens in nuclear fission. The uranium atom, once hit by the neutron, splits into two smaller atoms. These are called fission products. But that's not all. The splitting also releases additional neutrons and a tremendous amount of energy. Why do we care about these extra neutrons, you may ask? Well, these neutrons can then go on to strike other uranium atoms, causing them to split and release more energy and neutrons. This creates a chain reaction, and it's this chain reaction that is the true power behind a nuclear reactor. It's like a domino effect, but instead of falling dominoes, we have splitting atoms, and instead of a gentle tap, we have a burst of energy. Now about this energy, it's released in the form of heat and radiation. The heat is what we're really interested in here. It's this heat that is harnessed to generate electricity in a nuclear power plant. But how exactly is this done? We'll get to that in a bit. Before we move on, it's important to note that controlling this chain reaction is crucial. If left unchecked, the reaction can escalate quickly, leading to a release of energy that can be, well, catastrophic. That's why nuclear reactors are designed with multiple safety systems to control the rate of fission. So there you have it, nuclear fission in a nutshell. A neutron strikes a uranium atom, causing it to split and release additional neutrons and energy. This energy, in the form of heat, is what we use to generate electricity. But how exactly does that happen? Let's find out in our next scene. The heat released during nuclear fission doesn't directly produce electricity. It's a bit more complex than that. Let's break it down. Picture a kettle boiling on a stove. The heat from the stove turns the water inside the kettle into steam. In a nuclear reactor, it's the intense heat generated by nuclear fission that does the same job. But instead of a kettle, we have a massive pressure vessel filled with water. The heat produced during nuclear fission is immense. We're talking about temperatures higher than the surface of the sun. This extreme heat is used to boil water and create steam. But this isn't your everyday steam. The pressure inside the reactor makes it superheated steam, which is much hotter and contains more energy than the steam you see coming out of your kettle. Now this superheated steam needs somewhere to go and something to do. That's where turbines come into play. These aren't your average windmill turbines, they are massive, precision-engineered machines designed to convert the kinetic energy of the steam into mechanical energy. The superheated steam is directed onto the blades of the turbine, causing it to spin. The spinning turbine is then connected to a generator. As the turbine spins, it turns the rotor inside the generator. The rotor is surrounded by a coil of wire, and as it spins, it generates a flow of electrons. This is the basic principle of electromagnetism. The flow of electrons is what we know as electric current, or in simpler terms, electricity. The steam, after doing its job turning the turbine, is then cooled down and condensed back into water. This water is then returned to the pressure vessel to be heated up and start the process all over again. This is a continuous cycle, a beautifully orchestrated dance of physics and engineering. And voila, we have electricity, but that's not the end of the journey. The electricity then needs to be transported to the power grid, ready to light up our homes and power our devices. But that, my friends, is a story for another time. After the steam has done its job, it doesn't just disappear. It embarks on a new journey, one that is just as important as the role it played in spinning the turbines. This is where the cooling system of a nuclear reactor comes into play. The cooling system's role is as crucial as any other part of the reactor. It's like the safety net, catching the high-energy steam and taming it back into water. But it's not just about cooling down. The cooling system is also a recycler, ensuring the water is ready to be reheated and steam-powered all over again. To understand it better, imagine a marathon runner. After a long, strenuous run, the athlete needs to cool down and hydrate. Similarly, the steam, after its high-energy run through the turbines, needs to be cooled down and transformed back into water. The cooling system achieves this through a heat exchanger, a device that transfers heat from one medium to another. In this case, the steam passes through the heat exchanger, where it loses its heat to the cooler water on the other side. As it cools down, the steam condenses back into water. Now, this water isn't immediately sent back to the reactor core. It first needs to be treated and purified to remove any impurities or traces of radiation. Once it's clean and safe, the water is then returned to the reactor's core to be reheated and start the cycle again. This constant recycling and reusing of water is not only efficient but also environmentally friendly. It ensures that the nuclear reactor operates sustainably, without the need for constant fresh water supply. But it's not all smooth sailing. The cooling system needs to be meticulously monitored and maintained. Any malfunction could lead to overheating of the reactor core, which could have catastrophic consequences. So it's clear that the cooling system doesn't just play a supporting role, it's an essential character in the nuclear reactor's story, ensuring the system's safety and efficiency. A nuclear reactor is a finely balanced system, where every component plays a crucial role. So, in a nutshell, that's what happens inside a nuclear reactor. We've taken an enlightening journey, shedding light on the inner workings of these fascinating powerhouses we call nuclear reactors. The process begins with nuclear energy, a form of energy stored in the center of an atom waiting to be unleashed. And unleash we do, through a process known as nuclear fission. The nucleus of a heavy atom, like uranium or plutonium, is split into two or more smaller, lighter nuclei. This process releases a tremendous amount of energy in the form of heat. But how does this heat become electricity, you ask? It's all about harnessing the power of steam. The heat generated from nuclear fission is used to heat water, transforming it into steam. This steam then drives a turbine connected to a generator, and voila, we have electricity. Of course, let's not forget the critical role of the cooling system. After the steam has done its job, it needs to be cooled and condensed back into water, ready to be heated once more. This cooling process is vital to prevent overheating and potential meltdowns. By understanding these processes, we can appreciate the immense scientific and engineering feats achieved in our nuclear reactors. We can also better grasp the challenges and responsibilities that come with harnessing such a powerful source of energy. Next time you switch on a light, spare a thought for the complex processes that make it possible.